Thank you, David, for the introduction. This talk is going to cover mostly the work that they presented at ICSI. So this is more about the human side of refactoring. Refactoring is known to be a common practice in software development. This has been shown by previous studies. Programmers refactor their code frequently. This is an example of extract method refactoring, which can be done either manually or using a tool. Today, modern IDEs support many refactorings. The first refactoring tool was developed about 15 years ago. Nowadays, pretty much every IDE supports many refactoring. Here are the refactor menus of 3 popular Java IDEs: Eclipse, IntelliJ, and NetBeans. And as you can see, the list of supported refactorings is pretty long. On the research side, there is much interest in automating more kinds of transformation. Typically, they identify a recurring transformation in a particular domain and offer an automated tool for performing that transformation. These refactorings apply to various domains like parallelism, security, file implementation. However, recently it's been shown that programmers do not use these tools as much. So Murphy-Hill and others showed in 2009 that the underutilization rate of refactoring tools is about 90%. And this is based on a sampling of about 80 commits of 2 Eclipse projects. So it sampled a few commits and compared it with the Eclipse refactoring history and decided which refactoring has been done using the tool and which ones have been done manually. And it turns out that about 90% of refactorings have been performed manually in spite of the tool support. So this raises questions of why people choose to perform refactoring manually, even though tool support exists for it. And that's what derives our study. We wanted to answer the question. So to answer this question, we conducted a field study which had both quantitative and qualitative components. We developed 2 data collectors to capture the refactoring events, and we asked 26 programmers to install our data collector and use it for about 3 months. We collected about 3,000 refactoring events during 1,200 hours of programming from these programmers. Then we followed up with some of the programmers. We interviewed 9 of them for about an hour. So let's talk about a little bit about our participants. We had 26 programmers. 10 of them we recruited by contacting all the mailing lists of open source projects, and the remaining 16 were recruited from the University of Illinois. These were either graduate students or summer research interns at UIUC. So as you can see, about 18 participants out of the 24 that filled out the survey had at least 5 years of programming experience. So here's an overview of what data we collect. On the left-hand side, you can see an example of the data that Coding Spectator collects. At the top, you can see an example of the extract method refactoring performed on a statement of the print info method. And at the bottom, you can see the data that Coding Spectator collects for this refactoring event. It captures a timestamp, the kind of the refactoring, which is here extract method, the configuration settings, what the user has set on the refactoring wizard, the code snippet around the selection, the actual selected text, the invocation method, and the status is any error messages that the refactoring tool reports to the programmer. Navigation history records the time that every button on the wizard is pressed. This allows us to measure the time the user has spent on the refactoring wizard. Items marked as 1 to 3 are already captured by Eclipse. We added the attributes 4 to 7, and we captured this data by instrumenting the Eclipse source code. On the right, you can see another data collector called Coding Tracker. Coding Tracker captures every edit in the Java editor. Any deletion or insertion of a character, it captures it as a change and records it, and then we can later replay it to reproduce the state of the program at any point in time. So use this data collectors to collect our quantitative data and also to prompt our interviewers about the refactoring activity. So we use it to show them this is the refactoring that you did, and to remind them about their activities and ask them questions about their specific activities. So both of our data collectors are open source. We framed our results in a well-known framework in the human automation interaction community as disuse and misuse. So I'm going to present the results in 3 sections. The first one being use, which refers to a programmer using a refactoring tool to perform a transformation that could have been done manually. So we have identified a popular method of invoking refactoring. You can see a screenshot of this method. This is called Quick Assist in Eclipse. You can select a piece of code and hit Ctrl+1, which invokes a context-sensitive menu that suggests the refactoring is applicable to the selected context. Then the user can single-click on a proposal and see a preview, and if he wants, he can commit and perform the refactoring. So just a quick show of hand, how many people have used this feature of Eclipse? Okay, 4 people are familiar, good. So we counted the number of times people performed refactorings using this feature. It turned out that 35% of refactorings were performed using Quick. Well, I should note that Quick Assist does not support all refactorings, but the ones that were supported by it were used 35%. Well, if you exclude renames from this list, the rate goes up to 65. So we think this is because rename is probably so common that people just use the shortcut key rather than going through the menu. This is a pretty significant portion of the refactoring invocation. 6 of our 9 interviewees know about this feature of Eclipse, so we asked them why you rely on it so much. Well, they gave us several reasons. This is a quote from one of them who says he liked the context sensitivity of this invocation method. The fact that it just suggests a subset of all the refactorings that Eclipse supports. This narrows the decision space, and menu is no longer cluttered. Well, the others mention other reasons for using this feature, like Quick Assist is keyboard-driven, and it doesn't require much configuration. Pretty much uses default options and lets the programmer tweak the result afterward. So some of the implications of this observation is that other IDEs like IntelliJ or NetBeans could have used this feature to attract more programmers to the refactoring tool. And also, Quick Assist could have become more visible if a small detector suggested it. So right now, some programmers do not realize that this feature exists just because no one notifies them about its existence. Code small detector would be a good place to notify people that this stuff. So the next category of our result is about disuse. Disuse refers to performing a refactoring manually in spite of the availability of tool support for it in the IDE. We asked our interviewees 3 questions about their familiarity with each refactoring. We asked them if they knew that Eclipse supported the refactoring. We asked them if they knew what the refactoring did, and we asked them if they performed the refactoring manually. So based on these interviews, we identified several reasons for disuse. The first one being need. Basically, programmers told us that they don't use some refactoring tool just because the refactoring is not very frequent and it's not worth learning the tool for performing it just a couple of times. As an example, they told us that extract and pull-up are typically more often used than inline and pushdown because they typically start from a simple design and gradually generalize it. So not needing the refactoring is one reason for not bothering to learn the tool. Awareness is the second reason. It turned out that programmers are not aware of the existence of many automated refactoring. So apparently when they are not aware of it, they're not going to use it. The third reason is naming. So something simple as bad name could deter programmers from even trying out the tool. So here's a quote from a programmer who says, if I don't realize, generally I don't try them if I don't know what they do. So, and identified as 7 of 26 automated refactorings had names unfamiliar to the majority of our interviews. An example is generalized certified. Names are just too technical and hard to guess their function based on them. So trust is another factor that determines humans' use of automation in general. Reliability is an important factor in people's trust in automation. And research in human automation interaction community has shown if automation is not reliable, the human operator is going to lose his trust in the tool and stop using it. However, another thing that has been shown is that if the automation is highly reliable, then the operator is likely to forgive the tool for rare shortcomings. And this seems to be the case for the refactoring. Although it's known that refactoring tools have many bugs, the bug repositories are full of bugs about the refactoring engine, and prior research has identified various problems with these engines. They are fairly reliable. And none of the interviewees mentioned the existence of bugs for not using the refactoring. But before our interviews, it mentioned usability problems, complexity of the UI, and the overhead of using it as reasons of not using the refactoring. So it looks like usability plays a more important issue, plays a more important role in the utilization of refactoring. Another major issue with the refactoring tools is their predictability. This is kind of counterintuitive because one would expect the programmer to use a refactoring tool for complex changes, because complex changes are more tedious and they're more error-prone, but it turns out that they are also less predictable. I mean, the refactoring tool for complex changes is less predictable. And programmers who want to maintain control over their code are less likely to use a tool that is hard to predict. So here's a quote from a programmer who says, if the thing that the refactoring tool does is so complicated that it isn't easy to figure out things that are all right, I'm kind of discouraged to use it. So we wanted to learn more about predictability, the effect of predictability on the use of refactoring. We decided to assess the complexity of refactoring tools. This is kind of challenging to assess the complexity. So we took the two different approaches, one quantitative and the other one qualitative. So the three of us rated the complexity levels of automated refactorings in Eclipse independently, and then we sat together and agreed upon some complexity levels. We rated each refactoring as either simple, moderate, and complex. That's our qualitative approach. Then we counted the number of times that refactorings in each category were performed in our data. And you can see the count in the count column and the percentage in the third column. As you can see, the majority of the refactoring tools that were performed were doing simple changes. 52% of refactorings that were performed were simple. And only 10% of refactorings were complex. So this is qualitative approach. We also took a quantitative approach by counting the number of lines and files affected by each automated refactoring. And it turns out that 82% of refactorings affected at most 6 lines, and 84% affected just 1 file. The majority are modifying a narrow piece of code. So there could be several reasons for it. Like, as I said at the beginning, there may not be enough opportunity for performing complex refactoring on the code. That could be one reason. And the other reason could be just the predictability. Like, the tools for complex refactorings are not predictable enough, so they are less often used. Refactoring tools provide a feature, perhaps, to make the tool more predictable. They allow the programmer to preview the change. Both Quick Assist and the refactoring wizard provide previews of the refactoring before work performance is made. However, we notice that people rarely preview the things. About 1% of refactoring is previewed, just 1%. And in some cases, Eclipse forces the preview, so the actual invocation of preview by the programmer is lower than 1%. So we asked programmers, why don't you use a preview? And they mentioned several reasons. The preview is pretty cluttered, so it's a significant overhead to read it and interpret it, so people typically tend to just perform it. So the first code mentions that he prefers to perform the refactoring and undo and redo it to examine the effect of it on the code rather than studying the preview. And the second code is saying sometimes it's easier just to perform the refactoring manually and evaluate the design as I go rather than spending time previewing the change. Another barrier to using the refactoring tool is the configuration overhead. Here is the configuration dialog of the extract interface wizard. We measured the time that people spent on the refactoring wizard as a proxy for the configuration overhead. 82% of the configuration time of performed refactoring were at most 8 seconds. So this is a pretty short period. It kind of shows you the amount of time that people tolerate on a wizard. And if you look at the less frequently used refactorings, like pushdown, they have a pretty high configuration time. Like for pushdown, it's about 39 seconds. So configuration dialogues distract programmers from their interactive editor and force them into a modal dialog, which is kind of disruptive to their programming workflow. So identified awareness is one reason programmers do not use refactoring tools much. Perhaps a good idea would be to facilitate programmers' exchange of the knowledge about refactoring tools. Previews are not effective in making the refactoring tools more predictable, so we need to investigate alternative methods for reviewing refactoring, and we should come up with seamless configurations to reduce configuration overhead. So the last category is we define misuse as using the refactoring tool in a way that is not recommended by the designer. Here's an example. So the refactoring tools check a few preconditions before doing the refactoring. If the preconditions don't hold, then behavior of the program can change, or there may be compilation problems. So they will warn the user about the problems and rate them as warning, error, or fatal error based on the severity of the problem. When the refactoring tool reports a warning or an error, it's no longer guaranteed to be. But surprisingly, most of the time, people go ahead and perform the refactoring, even though it's not guaranteed to be behavior correct. As you can see, 88% of refactoring that issue the warning were performed. 68% of refactoring errors were also performed. So this kind of this implies that behavior preservation may not be the top priority of programmers in using the refactoring tools, so perhaps we should consider other aspects like predictability or the configuration in the design of these tools rather than focusing too much on the behavior preservation. Here are 4 of the 15 most frequent refactoring messages. The most frequent one is a warning that says code modification may not be accurate as affected resource has compiled errors. So people typically ignore this message and just because the message is not very detailed, it doesn't give you enough information about what to do with it. And at the bottom you can see another warning which says a variable name is already defined in visible scope. This is something that could affect the behavior of the program because of change to the binder. Another example of misuse that we identified is an unjustified use of the tool. Here the programmer is using a refactoring tool, change method signature, to modify the access modifier of a method. So we thought the use of the tool for doing such a simple change was kind of proprietary. So we asked the developer, why did you choose to go to refactor menu, select this refactoring, and then configure it, make a change that you could have done manually very easily. So the developer told us that we would like to use a refactoring tool wherever possible. There are cases where using the refactoring tool for even such a simple change makes sense, where there are corner cases and there might be a risk to change the case of the program. But the case we're talking about was a simple case and it was not justified to use the tool. So we kind of thought that this might be an overview tool for very simple cases. So our data shows that programmers tend to ignore warning error messages. Perhaps one way to reduce this kind of misuse is to reduce this rate of false warning, so that we are producing relevant messages that programmers should take seriously. And it might be worth investigating other methods of providing safety. Like instead of just reporting messages and errors, we could let the programmer continue with the refactoring and validate the refactoring afterwards and guide them in fixing places that might be intentional. So the refactoring tools have their own limitations. Their checks are not perfect. And to avoid excessive trust in these tools, we recommend that trainers warn programmers about the limitations of the tools so that they can use them appropriately. So like any study, our study has its own limitations. I'm going to go over a few of them. Some of our participants who are at the university, there's always a question of how representative of real programmers are these participants, but we think that they were close to professional status. Due to the uncontrolled nature of our study, the number of programming hours of our participants varied. This could have affected our results, but we did not report the results to the participants. Rather, we aggregated them and reasoned about the whole. Okay, so now I'd like to talk about some of our recent. These are not part of the XP paper, but some recent studies that we've done based on our previous study. So we wanted to rethink design of refactoring based on what we observed in our previous study. We consulted another source of refactoring data from the Eclipse Foundation. They collected refactoring events from hundreds of thousands of users over a couple of years, published it, took this data and we analyzed the refactoring data. On the left-hand side, you can see a graph that shows the number of invocations that refactorings are using. For example, you can see that 98.6% of the users invoked at most 50 refactorings. And on the right-hand side, you can see that 98.9% of these users used at most 5 different kinds of refactoring. So this shows you how limited the refactoring tool is in the wild. So we wanted to see how people perform complex changes. So we hypothesized that a way to do it would be to compose several smaller refactorings. We were mostly interested in more expert refactoring users, because we hypothesized that they are the ones who do complex changes using the tool. So we limited this data set to the expert users, those who invoke the refactoring tool at least 50 times and use at least 5 different kinds of automated refactoring. So we limited this data set to these users. As a result, we have a total of 112,000 refactoring events from about 1,000 programmers. We took the refactoring events and we picked a time window of 10 minutes. We put all the refactorings that were invoked within this time window in a single set, and then we ran a data mining algorithm to find the most frequent sets of refactorings in this data. Here you can see the table that lists the most frequent sets of refactoring. So one thing that can be seen is that programmers combine refactorings in a variety of ways. The second is that some combination patterns are more frequent than individual refactoring. For example, if you look at pull-up you see at the bottom, there are several composition patterns that are more frequent than the pull-up refactoring. So it shows the frequency of compositions of refactoring. Eclipse data did not have enough context, so we could not tell why people compose these refactorings. We could not analyze. So we consulted our own data set, which contains more textual information. It's a small data set, but has more context, so it allows us to understand the composition patterns better. Identify several functions, one being composition over configuration. So we notice people sometimes compose refactorings to avoid the configuration overhead. Like, instead of configuring the refactoring wizard for pull-up, to pull up 2 methods from one class to another, they perform 2 separate pull-up refactorings. This is going to reduce the configuration overhead by composing 2 refactorings. Another reason that we found for composing refactorings was doing refactoring design pattern. So there is no tool in Eclipse for refactoring to template method, so programmers instead compose extract method and pull-up to simulate this refactoring. Closely related entities. There are several examples for it. One that I think is that there are entities that are related but not by binding. For example, the programmer renames the field of a class and then goes off and renames the corresponding parameter of the method, of the constructor. So these are closely related but not related by the binding. So there are other uses, but I'm going to skip over it. So the lesson is that people are already composing refactoring. So we decided we thought, how can we leverage this practice to come up with another way of doing refactoring? We conducted a survey. We prepared mock-ups of our tool and conducted an online survey asking programmers to compare 2 interfaces of refactoring. We picked a more complex and less often used refactoring tool of Eclipse, namely Extract Superclass, and we showed the screenshots of people to the participant. So here's the screenshot of the existing refactoring tool. We have a simple class, Daisy, with a single method water. Programmer opens the refactoring menu, selects the extract superclass refactoring, configures it, the first page of the configuration, second page, finally previews the refactoring, and performs it. The extract superclass refactoring is going to create a new class, flower, and move the water method from Daisy to the new class. So that's the existing interface. And then we showed our interface, which uses the composition style and quick assist to do the same refactoring. So here's class Daisy with a single method. The programmer invokes the quick assist menu, selects first action, which is create a new superclass. An empty superclass will be created in the file. The programmer can rename it flower, and then select the method water and move it to the immediate superclass, which in this case will be flower. Now we have the two classes in the same file. There's another action to move the type to a new file. And finally, we will get the same result, having new class, a superclass of Daisy with one. So we conducted this survey and we analyzed the first 100 responses. It turned out that the majority of participants preferred the positional approach. We followed up with the lab study. The example in the survey was kind of simple because we wanted to make it accessible to programmers filling out the survey online. In the lab study, we used an example from the refactoring to design pattern book for doing the composite refactoring. So we took this example and applied it on an open source project, HTML parser, and we invited 13 professional programmers to try out the two different interfaces on this piece of code. The study took about an hour, so they tried the tools in random order, and then we asked them about each interface. We asked them which one gave them more control, which one they thought gave more confidence about the correctness of the refactoring, which one was easier to learn, which one was easier to use, which one they thought had more opportunity to use, which one they were more satisfied with. Again, most participants prefer the compositional style. So here are some qualitative comparisons of the tools. So we asked people to tell us what they liked and disliked about each approach. These are some of the codes. So this code is saying the second compositional style provides a more stepwise view, giving me more intermediate feedback as well as an ability to run my tests at each step. It goes a long way to making sure that refactoring is the right decision. So this supports our hypothesis that the compositional style is more predictable. Thus, it performs a small change at each step, and it gives more control to the programmer. So this is a complaint about the wizard. Wizard gives this illusion of just doing everything for me. The downside is that there were a number of options that I read didn't quite make sense of, that I guess I don't have to care about that. And of course, I found my sorrow that that wasn't true. It did things that I completely didn't expect, and it doesn't give control. Again, this is supporting what we found in our previous study about the unpredictability of these tools and the overhead of integration. So, but the compositional style has its own shortcomings. For example, here is a post from a participant saying that I often extract a common superclass from multiple classes and several methods. So nice that the wizard can operate on multiple entities, multiple method classes. Something that is kind of difficult to do using the quickest approach. Another comment is that since compositional style is doing these transformations in the smallest steps, and they are kind of independent, tool does not have a good view of the big picture. So the concern here is that the refactoring may not be complete. On the other hand, the wizard can kind of provide some level of guarantee about the completeness of the refactoring. So these are some advantages and disadvantages of the two approaches. Overall, we think the compositional style is a good complement and is likely to improve the utilization rate of refactoring. So I'd like to finish up with a few takeaway messages. I think these studies show that automating complex refactoring is more than rewriting code and providing behavior conservation guarantees. We ought to think about usability issues like predictability or making people aware of tools and configuration costs to really get people to use the tools to become more productive and do transformation with less errors. And our studies show that programmers prefer compositional refactoring tools over the monolithic one. We think that this is a good alternative way for doing complex changes in a predictable way.